Hi, Stella.
Hey,
How are you doing?
good. How are you?
Fantastic.
So
Yeah,
I
thank
picked this time because I thought this will be after CVPR submission.
you.
But then the
Oh, yeah.
deadline extended, and now we are between Eclair and CVPR. So
Yes, yes, yes. It's a very busy time. I completely understand that. We really appreciate that you accepted to give this talk.
no, I
Yeah,
appreciate everybody showing up even for my talk.
right.
Yeah.
Absolutely. And so we have classes ending at 12:05, and the students,
Okay.
it usually takes about 10 minutes, 10, 15 minutes for the students to come in. So we will start at 12 15.
No
Is
problem.
it right, or 12:15 or 12:20?
Yeah. No problem.
Uh,
Let me know.
Fantastic.
Somehow when I see my talk, I don't see any of you. So I'm trying to get it back.
Okay.
Maybe gallery. I think I have, right. Let me try again. I don't see you guys anymore. Um, can you see my slides stepping forward?
Yes. Yeah, we see your slides.
If now, do you see the next slide?
Yes.
Okay. Okay. The only thing is I'm not seeing video of you. For now, it's okay. Once I'm done with the talk,
If
I can stop sharing, I guess.
Yeah, and if there are any questions, we can read them for you. We can stop and read them for you from the audience. Yep.
Okay, okay. Uh, I'm not seeing any of your videos, like the persons. So yeah, so I think it's fine. Once I'm done, I can stop sharing. Maybe then I can see the gallery of people.
Sounds good. Fantastic. Hi, Tyler. Oh, hi. Okay, great. So now that all the panelists are here, maybe we can start. Hello, everyone. Thank you so much for being here. Today we have another Vanderbilt machine learning seminar. We are very excited to host Stella Yu. Today, Stella received her PhD from Carnegie Mellon University, where she studied robotics at the Robotics Institute and vision science at the Center for the Neural Basis of Cognition. Before she joined the University of Michigan as a faculty in fall 2022, she has been the director of Vision Group at the International Computer Science Institute, a senior fellow at the Berkeley Institute for Data Science, and on the Faculty of Computer Science, Vision Science, Cognitive and Brain Sciences at UC Berkeley. Stella is interested in not only in understanding visual perception for multiple perspectives, but also in using computer vision and machine learning to automate and exceed human expertise in practical applications. Stella, we are very excited that you accepted our invitation, and we look forward to listening to your talk.
Thank you so much for the invitation. And I know everyone's busy with ECLEAR or CVPR, so I appreciate everybody making time and coming to my talk. Okay. Okay, so let me hide meeting control. Okay. Okay, today I'm going to talk about unsupervised learning of segmentation by recognition and for recognition. Now, since it's going to be a segmentation talk, I want to start with the so-called state of the art. And this is one of examples given at the SAM, segment anything model, given image, a painting like this, and they are able to provide such a segmentation. It's an amazing result. You know, the method itself is trained on 1 billion masks on 11 million images, okay? And you can see that the architecture is relatively simple. It has an encoder, and it goes through some convolutional feature processing, and it accepts the points, box, and text, and then it outputs 3 different levels of 3 different kinds of segmentations. If you are interested in, if you have a point on the scissor, you will see the whole scissor or the part of the scissor. Okay, so it has already acknowledged there's a granularity in segmentation, and they try to cope with this, because when you deal with segmentation at such a scale, the ambiguity is inherent. Now, and you can see that people hail SAM as this revolutionary foundation model for segmentation. So is segmentation done and over in computer vision? Now, here's an example. What do you see in this image? There are, you know, different people see different things. If you're in person, you know, it depends on the distance you are sitting from the where you're sitting, right? You may see 2 possibilities. One is you see old man, okay, and another and you can see this part on the lower left corner. That's the hand of this old man resting on the chest. Some people may see there are, in fact, an very old man on the left and a woman carrying a baby on the right. Okay, at these different scales, you might see different things. Now, if I submit this image to the state-of-the-art image captioning methods, for example, Blip, it will give a captioning, a painting of a man with a beard and a red dress. Okay. And if you ask SAM, and these are SAM's results at a different grid levels. Okay, obviously it does not see the old man, and this is a painting by Octavo Ocampi, and this is metamorphical art where he's trying to illustrate that the old general comes from very humble beginning with an old farmer father and farmer's wife. Okay, and he captured everything into one painting. So this result illustrate that segmentation is never about you know, it's never a piecemeal analysis of an image, right? It depends on what you are focusing on. It depends on the sort of scale attention and the holistic interpretation. When you see the old farmer with the woman carrying a baby, the previous hand becomes a dog lying on the curb. Okay, so all the meanings, interpretation, segmentation changes. Okay, this is not something that Sam can do. Now, my talk is about unsupervised learning or segmentation. Sam achieved amazing results with the supervision. But what if there's no supervision? What can we learn from nothing but data? Here, I show you some example video clips from YouTube of US. When we look at these results, you feel you can grasp each video content very quickly. A woman carrying a baby, walking on beach. You know, I have to constantly remind us, when we are developing machine learning algorithms, computer vision algorithm, we have to think of the distinction between baby vision and grown vision. Our neural network equipped with none of those concepts is very different from a grown vision. When you see a video like this, it's sort of black and white world. You have concepts. You know what a brown elephant against the green grass is. You have already done this chunking of information. But for baby, all the information, what happened? All the information it gets is this flickering of light, which is very distracting. It has no sense whether the light change comes from illumination or comes from the movement of objects in the scene. It has no concepts of objects. So this problem, unsupervised learning, I liken it to this figuring out what's in a boiling, sizzling soup, right? This is what the father of psychology, William James, says: blooming, buzzing confusion. The baby is bombarded with a lot of sensations, vision, auditory, even visceral, internal sensations. And it is trying to make sense of this, what these sensory signals are telling us. And pretty much like, we have this soup, everything mixed together, but yet we need to tease out, there's this taste of garlic, basil, tomato, so on and so forth. So in a way, we need to go from this undivided sensation, we don't have any idea of what they are, to this bounded rationality. The world is not random. There are finite concepts out there, and how we can make sense of it without supervision, because you can't tell baby, this is a cat, this is a dog. All of these supervision is not feasible. So the first work I want to talk about is our unsupervised learning or generic objectness. Given videos, just videos, no labels at any level, not at the clip level, not at pixel level. We want to be able to put a hotspot on the objects. Object meaning concepts that potentially occur often, and but we don't know what they are. We just know they are sort of objectness. So in computer vision, this is called video object segmentation. And if you look at the videos on the left, you have, I don't know why the videos are not playing, but why the videos are not playing? Okay. Something is not right here. But okay, on the left, you can see that even for video like this, the elephant is moving. You think it's not a hard problem. Even based on color, you can segment it. On the right is actually a fish, is a camouflage fish moving in this background. If there's no movement, if I don't outline this in green, you will not be able to tell there's a fish, right? Only when the fish starts to move, you start to see the moving object. So there are these two extremes. And in between, you have both phenomena. On the left, you have appearance-based segmentation. On the right, the motion provides you the clue of segmentation. In between, the giraffes, all they move together, even though the legs and head, they are moving at different speed. Even the textures are different. The bottoms are white. The top, you have spotty textures. Somehow we see them moving together as one foreground. And obviously, motion helps us, but sometimes when you deal with this additional cue of motion, it also introduces complexity. And this one, you can see that, this alligator is supposed to rotate in depth, and the color is more or less same as the background. It's difficult. And the second video, supposed to be video, and what you see in individual frame is not what you get from video where you have blurring. When you consider motion cues, the cues may be conflict with what's in the individual frame. And then there's too much motion, so much flickering, and you don't know, it decreases the signal to noise ratio for the foreground. Okay, so from computer vision point of view, the problem of object segmentation is as following. Given an image sequence, we want to be able to segment each frame into foreground versus background. Now, traditionally, this work is when you have a sequence of images, people think that adjacent frames will give you optical flow information. Okay, so then this problem becomes a multi-cue integration problem. Appearance gives you one clue how to segment each image, and optical flow tells you what moves may correspond to an object. So you kind of want to massage two sources of cues together and output that segmentation. What we trying to do, we don't introduce additional source of input. We actually introduce additional output, unknown output. We not only want to get the segmentation, we also want to get the segmentation flow, okay? How each segment moves, okay? So it's like initially I'm only solving one set of unknowns, but now I introduce another set of unknowns. Somehow there are constraints between them, and this allows me to solve both more effectively. So let me illustrate the concept. What is flow? This textbook explanation, there's frame 1, and then the horse moved, we have frame 2. And based on where it comes from, you can figure out how each pixel moved from frame 1 to frame 2 in the image plane. And the optical flow is simply the local displacement per pixel. And if I denote the first image as I, the second image as J, you can see that they're related by the pixels correspond by the displacement delta x. And the criterion simply is to minimize the discrepancy between these two corresponding pixels. And this is usually done for a specific image pair, and it's independent between pixels. That's the basic version of optical flow. Now, what we are doing is that we assume that the world is not random. It is made of few segments, and every pixel in the segment move together, okay? So we have the same criteria. We want two images, their corresponding pixels, the appearance at the two corresponding pixels should match. The only difference is we minimize this loss over all training pairs. We want something that statistically making sense. And we assume that the flow for each pixel is the same in the same segment. This idea seems very intuitive, but the problem is that we don't know the segmentation to begin with. If we have the wrong segmentation, this assumption doesn't hold. So our idea is to concurrently learn segmentation and the flow together. Given the image, we have a segmentation network that will spit out a segmentation, but we don't have ground truth. We don't know what the ideal segmentation should be. Given two images, we are going to estimate the flow. If we have the segmentation, if we have how each segment moves, we should be able to copy and paste and predict what the frame should be in the next time step. And for that, we can close the loop. We can minimize the prediction and the actual frame we got in this reconstruction error. So here's some more details about the method. Given image, we have a simple segmentation network spits out pixel-wise softmax scores. You can think of here illustrated 3 channels. In the model, we choose 5 channels. The top stream takes 2 images in, calculate the feature, and can calculate the correlation volume between the 2 sets of features. And then based on the segmentation we have in each channel, it's a soft segmentation in each segmentation channel, we can make a prediction about the average flow in that segmentation channel. And now we broadcast the segment flow to every pixel, and we just do simple copy and paste. There's no decoder, okay? So given this, we can actually do copy and paste, predict, synthesize the next version, and we minimize this loss. So we train on YouTube VOS. It's a previously curated data set by some other people. There are about 4,000 videos. You can think of roughly, we only have 4,000 scenes. Each is roughly 5 seconds long, and it covers 94 categories illustrated here. Now, because our segmentation only needs 1 image, it can spit out a segmentation per image. We can ask what the segmentation is like. So given the image in the first row are 5 segmentation channels with spit out the segmentation, you can see the first channel seem to indicate the object of interest. We don't know that, right? This is completely unsupervisedly learned. We don't have ground truth for segmentation. We don't have ground truth even for the flow. We don't use optical pre-trained flow. It's just that we set the segmenter and the flow estimator as players on stage and let them perform so that their results can be synthesized to predict the next how the next frame should look like. Now we look at another image. You can see the first channel seem to capture the person. And there's one more example. Now, at this point, we were very surprised because when we design the model, we have 5 channels in the segmentation stream. But these 5 channels were born equal. We never specify the first channel you need to encode foreground and background, right? But somehow all these examples we look at, this channel seem to signal where the foreground is. And we look more into it. This channel may change, depends on how you initialize it. When you have the random seed to initialize, the channel may move around, but we can identify this without any labels. And this channel tends to correspond to the largest reconstruction areas, because between foreground and background, if the background, you can see all the other channels, they break the background into different areas. If some of the background, the segmentation is off, the reconstruction error won't be much worse. But between foreground and background, a slight difference, if the flow is off, then the reconstruction error is very large. So we find that the objectness emerges in a particular channel, even though we did not design the model to have that property. Now, so we can, given a set of videos, we learn our segmenter and the flow estimator, and we can identify that channel. And then at the test time, given a particular video, we can continue to fine tuning, so-called test time tuning, because the criterion doesn't require any labels for this particular video. Let me see if this works. Why is not working? Somehow my video is no longer playing. But anyway, these are actually from different data sets And we can see that as when the video moves, you see that the video is doing our segmentation is doing a very good job latching onto the object. Because our segmenter is only is single image based, it only requires one image. We can also apply the model to single images. You can see that this is from DUTS as an image saliency data set we have never ever seen. And for these results, you might think that's not surprising. Oh, the foreground tend to be humans, cars, animals. They seem to be moving objects. But here, there's a last column. You can see there could be statue, plate, bench, so on and so forth, even boulder, even plaque on the facade of the building. And so we were really kind of pleasantly surprised by this discovery. This work shows that figure ground segmentation can be learned without any preconception of edges, optical flows, or saliency. The only assumption we make is that there's instantaneous visual constancy. The world has not changed dramatically from one frame to the next. There's only a slight change, and the world is only made of finite segments, and the segments move in the visual world. Any questions?
So yeah, I have one, Stella. So this can be formed as an optimization per image, if I understand correctly, right? And the optimizer is parameterized. So the segmentation is parameterized as a neural network. So we have a neural network that we are optimizing to solve the segmentation, correct?
Yeah.
Yeah, and so then is it fair to, when you are training it on all the videos, it's very much like meta learning. You're finding a set of parameters that does a fairly good job for all videos. And then when you get a single video that you want to do the segmentation, you keep fine-tuning on that. The test time optimization that you mentioned is you keep fine-tuning on the specific video to improve the segmentation for that video, correct?
Yes, yes. So in a way, people, even in human vision, people knows that motion is a very strong cue for us to identify, to develop the concepts of objects. But this kind of remains at a hand-waving level. This work is kind of a computational realization. So in our model, we don't have supervision in each pathway, the segmentation pathway or the flow estimation pathway. But they have to work together in order to reconstruct, make sense of the world. So you see when will the reconstruction error be small? Two things have to happen. First of all, the segmentation need to conform to the moving objects. Secondly, the flow has to be right? So that's a very strong constraint on the system. So and then once, if I don't have the motion pathway, the segmentation.
Can you hear us? Yes.
I'm back.
Yeah, we lost you.
Wi-Fi, Michigan's Wi-Fi is gone. So I'm using my cell phone now. I don't know why. That's no wonder it's so sluggish at the beginning. But anyway, where was I when I dropped off?
We were talking about this idea of the temporal consistency in the movements, right? Like exactly at this slide, correct?
Okay. So I was explaining that in order for the during training, the loss will be small only if two conditions are satisfied. One, the segmentation is correct; they correspond to moving objects. Two is that the flow estimated is correct. So if you only do the bottom segmentation, the segmentation will pick out similar features going into the similar the same object, right? Same region, but it doesn't have to be, the moving object. By asking that the two have to lock hands and they have to synchronize with each other, I'm capturing the concept where the moves tend to be the objects. This is kind of transfer the moving aspect into the segmentation network. I distill that knowledge into the formation of the object segmentation. And people, even in human vision, people always know that motion is very important for babies to learn, concepts of objects, but it remained at hand waving level. There's no good model to actually demonstrate it, in experiments. I think this is the first attempt at this.
I see. So if I then like the follow-up question is the surprising finding here that you mentioned is that foreground is the one that foreground in this video. So move more, or otherwise we have this.
Not move more. The reconstruction error is large, so I can identify that channel. So right, in a way, initially I would have thought different segmentation channel will be in charge of different appearances, right? That's a reasonable assumption. But somehow everything condensed into one channel. Why is that? That channel has commonality. This is the one that the syncs with the flow estimation, right?
Yeah, but doesn't that mean that essentially like we have more movements because like our error is larger?
That's true. That's true. You're right.
Right.
They also the movement is large. Yes.
I see.
Correct.
If I have a video that the camera is fixated on the object and the background is moving, like
yes.
Like
right. So in fact, I hope does this work. FBM's S53, the third column has a lot of camera jittering. We can still latch onto it.
Oh.
Yeah. Yeah. So unfortunately, why? I don't know why. But anyway, in light of time, I want to so just take my word for it. Somehow the model handles this. It doesn't differentiate ego motion or object motion. Okay, great question. Now I want to move on to the second piece of work: unsupervised learning of hierarchical semantics. Okay. So hold on again. Let me. Okay. Let me hide this. Okay. Okay, so when we want to work on unsupervised segmentation, the first problem we encounter is how do we know we are doing a good job? See, in supervised learning, this problem is avoided. This is a scene from MS Coco. And you can think of the way I construct it. If there's an underlying passing tree, the top level is, say, foreground, background. The left branch may be, the foreground, and the right is a background. In the foreground, there's, persons, okay? And in person, you can further divide into legs, torso, so on and so forth. On the right, you could have curbs, grass, rocks, so on and so forth, okay? So you can think of, in this particular data set, when people in COCO, they annotate, they pick these, in this passing tree, they pick this level, these are colored nodes, okay? In the same, for the same image, in dense pose, they are picking different set of nodes. They only care about the decomposition of a human body into different body parts. All the background, the curb, grass, and rocks, they don't care. It's this black node, okay? So semantics intrinsically has multiple levels of granularity. So what's the target of our unsupervised segmentation? How do I know that we are doing a good job? We don't have a target. So that's the first problem we need to solve. So we take this segmentation as a pixel-wise representation learning problem. The idea is that given an image, if I can learn the right feature, X, if I have the feature, I can do grouping in the feature space. And those that fall in the same group will belong to the same segmentation. So I induce a segmentation in the image. Now, if I have the segmentation, I can try to learn the feature that supports such a segmentation so that the pixels within the same region has similar features. Between different regions will have different features. So that's a feature learning problem, okay? Now, the problem is that in unsupervised learning. We don't feed these two. But our insight is that any good feature should make segmentation consistent. Am I still online? Hello?
We lost you a little bit, but now we hear you. Yes.
Okay.
Now it's fine, but
yeah, I see it gives the internet unstable. Anyway, okay, so the idea is this: given an image, let's say there's some oracle ground truth we don't know. And of course, this can be, some at the different levels of granularity, finer segments versus core segments we have no access to. Let's say we do augmentation, flipping, color, grayscale, and all of that. And we can do multi-view co-segmentation. Let's say each will give us this segmentation. We don't know that, but when we ask for more segments, supposedly this corresponds to fine grouping. And if I do clustering transform, I don't allow arbitrary. I don't have free license to re-break and recombine. I can only recombine them. Then I have a coarser segmentation. So I don't have access to the ground truth, but what I can ask for is that I want the coarse grouping and fine grouping to be consistent. Okay, I don't have ground truth for each, but I have a desired property between them. If a segmentation can have that property, I think I'm not too far from the actual ground truth. So this is the learning diagram. Given an image, we try to find a pixel level feature with the CNN, and we find a base cluster, and we can learn another fine cluster feature. This mapping is through this transition matrix learned through so-called clustering transformer, and the clustering in the feature space will induce segmentation image plane. We only have two losses. One is a feature learning loss. The other is goodness of grouping loss in the image plane. So this is just show that, even though we have this consistent hierarchy in mind, even on flat semantic segmentation, because that's what people usually benchmark on, we outperform. Them, you can see our gain is substantial.
Stella, could you repeat, because we lost your voice for a second on this slide? So you
This slide is to show that this is unsupervised trained with hierarchy in mind. But in order to benchmark this method, and all the existing benchmarks are on the flat organization, right? It doesn't care about hierarchy. So benchmark on those, we are better than the existing approaches when we publish the work. Okay, so meaning that even asking this property consistent across scale can deliver substantial performance gain on flat semantic organization segmentation. But the key thing is we can do hierarchy. We can do first unsupervised hierarchical semantic segmentation. If you ask me for 3 segments, that's our result. 6, the second result. 12 is another. You can see that it's a continuous refinement. Oh, sorry. On the left is the previous method using the BSDS human annotated boundaries. It only cares about the strength of the contrast of the boundaries. On the right is our results. So you can see the top, we already identified the 2 sheep actually belong to the same group, and then there's a refinement, okay? And we can do some benchmarking for object in this manner. You can see that we are better than others in terms of, they are not a lot hierarchical, unsupervised hierarchical semantic segmentation. So the left is earlier work, based on the annotated boundaries. Now, what I find very interesting is that we actually have features at a different scales. And our method produces segmentation for each image. And for each pixel, we have a segmentation. So we can do unsupervised segmentation on the top. And you can go for the next level. So we can pick out the group of 3 players. If you go for final level, we can pick up the top torso and the bottom legs. And we can do retrieval. In gallery, we can also compute the segmentation and pixel features. We can retrieve these nearest neighbors. That's amazing results to me, because the appearance of the layout changes so much, yet we can identify these at the top K nearest neighbors. We can do the same thing in the features space at a different scale. We can traverse basically features across scales. Okay. The third work, I'll take question after this work, so they're related. Unsupervised learning of visual context. So if you look at the annotations on these scenes, you can see that, for example, these different colors means different semantics. When a person is on the bike, it's called a bike rider. When a person is walking, the bike rider has a very fresh, brilliant red, and the pedestrian has a darker red, because they are now called pedestrians. And you can see the road and the sidewalk, they're all different, right? So in a way, when we do supervised learning, we give different names. Names are not as important. It's the same person, walking on the road. When they get on a bike, it becomes bike rider. It's really not the naming, it's the grouping, what context this concept is embedded into. So this has implication on human object interaction recognition. There's this HICO data set, and each action is described by a subject, a verb, and an object, right, and a noun, such a phrase. So how would you do it in a supervised learning manner? That's the usual approach. You have an image, you have feature maps, you have detected instances, and then you combine the two together, and you can identify person, drink, a bottle, that becomes your, that fits your labeled data. So that's how this is usually done. But the problem with that is it's impossible to enumerate all interaction types. Just think about this combinatorial explosion, right? You can have different verbs, same verb, same person, you can hit different objects. This scales up pretty soon, you'll be out of control. So our approach is to do discriminative feature learning. So we are gonna go through a pixel-wise feature map, and it should support instant segmentation. It should support semantic segmentation. So here we assume we actually we have labeled concepts like person, so on and so forth, but we actually don't know the interaction activity, so on and so forth. We don't have the context labels. So here's how we benchmark if we are getting the context right. Suppose we have a ground truth label of the person in the middle, and we can create this 3x3 grid. And we know in the ground truth, each pixel's semantic label, we are going to do the histogram of the labels. And this label distribution is a proper feature and can be used for retrieval. And the bottom row shows how we retrieve by this ground truth semantics, which capture the context information around the center object. So what's shown here is that the orange line, if you focus on the left, the right is similar. It's just it's a supervised baseline I described, okay? Each action, person, action, object, noun becomes one label for an image. And that's a performance in terms of precision and recall. And the blue line is a supervised SOTA result, okay? And the red line is our results, our unsupervised context. Our model is only trained on COCO for semantic instant segmentation. We directly evaluate on HICO. We have never seen an image in HICO in the past. And we don't know what you are querying, testing me on. So the green line is the oracle I explained earlier using ground truth semantics. Okay. You can see that we have higher precision, right? Our local is a little lower. What does that mean? If we say it is something, it is true. But sometimes we may not recall the right term. For example, snowboarding. In the HICO data set, you take off and you land, they're all different actions. So if we, on the right shows that if we disregard the action type, we only see if we get the interacting object category right, you can see all the curves immediately move to the right, high precision and recall. So it's really this fine-tuned action, which is very hard to tell in a single image. So this sort of connects, so this is continued from the last work where we show that the image, the feature we learn, not only capture what the object it is, but also encode the context it is part of. And when we have such a learner feature, we can use the feature to retrieve similar instances. On the similar labeled instance, we will be able to figure out the proper context. Any questions? Okay. So, do you have questions?
No, there's no questions in the chat. I think like we can ask the questions at the end of the talk. Yep.
Okay, great. So the last piece of work I'm going to talk about, so the second supervised learning of hierarchical segmentation. My goal is still segmentation. That's my end task. What I want to do here is that, just like, Sam is treating segmentation as the end goal itself. I don't think this is the right approach to do it. What we explore here is that segmentation is really a stepping stone. Segmentation belongs to recognition. It's just tool recognition uses to accomplish its job. What we are trying to do is that with or without labels, okay, at image level, we will be able to learn hierarchical decomposition of parts and wholes. And this segmentation, this decomposition is useful for recognition. So let me explain. What do you see in this image? Now, for people who haven't seen this is a famous illusion, but if you haven't seen it, I also modify a little bit. You might think, oh, this is just an ink blob. There are 3 black ink blobs, okay? And for some of you, you may see this as a girl, right? And for others, you may see this as an old woman, okay? Now, this is recognition task. An image could take on different semantics. I picked this image because it gives you 3 ambiguous things, but you can think of in different settings that you can really associate different semantic words with one image. So recognition, you build a model to do recognition. That's a usual practice. And then there's also this segmentation task. And corresponding to ink, you might have this, all the ink blob is one group and the rest is another. And for a girl, you can see that I'm highlighting the face. For those of you who haven't seen the girl, you should be able to see it now because you can see the black is in the hair, the profile of the face is out. And when you see the woman, some people don't see the woman. Now I can tell you, the girl's chin now becomes the big nose of this old woman, okay? And this whole thing, she's wearing a scarf and so headpiece. You can see that segmentation is different. And traditionally, you will build different models, segmentation models for this task. If you treat segmentation as a separate task, different from recognition. What I want to point out is that people neglected that in segmentation, when I see this as ink, a finer granularity, you have 3 separate ink blobs. For a girl face, and for the woman, I can do the same thing. The thing is, if I recognize a girl, I will never see the segmentation of an old woman. When I see a woman, I will never see the segmentation of a girl. So the name of ink, girl, woman isn't important because this is just a name you give to the image. What's far more important is this internal consistency. between segmentations at different granularities. So what we are going to do is the following. Given a set of images in the vision transformer model, you have regular patches, you have patch tokens, you can repeat this few times, and then you go for a final class token, and you can impose some image discrimination. If you don't have labels, it's image-wise discrimination. If you have labels, it's a categorical discrimination. It's with a fixed size patch tokens and the same number of patch tokens throughout the network. What we're trying to do is that we start with the superpixels, and then we use graph pooling to gradually merge them into coarser and coarser segmentation. Recognition, which happens at the image level, is just at the tip of this pyramid. It's just the whole image, right? So segmentation and recognition, they are not different from each other. It's just at a different spatial granularity, okay? So with this scheme, even though we impose loss at the very end, at image level, we can learn the hierarchically consistent segmentation for free. Here, I want to point out that this is different from weakly supervised segmentation, where people try to learn the segmentation based on image level labels. For example, you say, this image contains cat, this image contains a dog. And the weakly supervised segmentation one, it wants to output the segmentation of cats and dogs after you see many other examples. Here, so there is about localization of known semantics. Our work, we are discovering internal hierarchical parts. Each part has a different semantics than the image level semantics. We are not localizing external named hosts. Our semantics is open, okay? So I'm going to demonstrate this in our results. So this is more details about diagram. Image comes in, we do superpixel partitioning. And so this becomes our starting point. Like the previous work, we are going to learn this successive graph pooling. And the pooling is learned in such a manner that at the end of the day, at the very end, it supports better recognition, okay? Internally, we never have any supervision for segmentation. So you can see that this segmentation is for the use of recognition. It is, it belongs to recognition. It's learned by recognition. Okay, and so here show three sets of results. You have image, the superpixel partitioning is below each image, and then we compare VIT is small with our work called CAST, concurrent segmentation recognition with the adaptive tokens, segment tokens. You can see that we, first of all, we are consistent, right? You can see the baby's head consistently picked out. There's a refinement of the torso into more and more segments as you go down finer grained segmentation. Likewise for the dog, right? The dog is made of different parts. As you go deeper, the legs may be differentiated from the torso. The torso may be broken into more parts. And what's more is that at the beginning, I mentioned that SAM is trying to handle this multi-granularity statistically. It gives three outputs at a different granularity, but it doesn't impose this instance-specific consistency across these granularities. So there is a data set called part image net. They labeled the wholes and the parts, and this is trained on unsupervisedly trained on COCO, and we just benchmark on the part image net. You can see that if the VIT version doesn't have concepts of parts and wholes, SAM is supervisedly trained with so many object annotations, but there's no consistent. At the top level, we have the orange and blue colors. At the bottom, we have the orange will turn into dark lighter oranges for the next level concepts. So is for the blue ones. You can see the refinement in concepts as we traverse the whole parts and whole hierarchy. And you can see that we are much better at picking out the objects as well as the part and whole decomposition. And here's another example. And we can benchmark this. We can do unsupervised discovery on parts and wholes. These results are not trained with any labels. We just use this self-supervised learning. You can think of MPID or MOCO. You just ask images to be different. Okay. And you can see at the category level, we are 14% better. At object level, we are, all there's substantial gain in MIOU and F score. And look at the G-flops. Our G-flops are much smaller because we are using not all those square patches, patch tokens. These are text-inspired vision transformers. This is super pixel-inspired transformer. This is a true vision transformer. Again, we do the same thing. A lot of benchmarks on segmentation on flat organization. So we show that we are also better at a flat semantic segmentation. And there are some results showing that we can do this self-supervised training on COCO, and we can do this, evaluation right on VOC. Before any tuning, we are better. And after tuning, we are better. On the right-hand side, it's a supervisedly trained on ImageNet, because you could provide the image level supervision, and we can still learn the hierarchy. And then we do the fine-tuning on individual data sets and show we are better. And in the left table, we also show, people always wonder, so our gain, where does our gain come from? Is it about us replacing the regular patches with our segments? Or is it because of graph pooling? And you can see from this ablation study with the VITS, both factors contribute to our better performance. So, and the last thing we've shown on the part and whole discovery on the flat segmentation. And the last thing is about recognition itself. Unlike other methods, we are doing concurrent segmentation and recognition. These are done end-to-end at the same time. Our segmentation serves the master of recognition. And during learning, it's learned by recognition criteria, minimizing the recognition loss. And what we deliver is the part and whole, which is better for this hierarchical part and whole recognition. So this shows that we are better, and most importantly, we are 30% more efficient in G-flops. So this is my last slide. Taking all of this in, I'm pushing for this mid-level learning, right? I think that I'm finding these jigsaw pieces, mid-level vision. It's not at the low level where you have pixels. So if you train on images with T-shirts, it doesn't work well in real world. If you train on, the cars parking on the street, then you have flooding and you don't know how to deal with this OOD or long tail phenomenon. I think the mid-level is the key to handle this low-level variations, domain gaps. And the mid-level is also the key to handle the whole range of different high-level tasks. It's not just for recognition, detection, segmentation, instance, or semantic level. It's about that once you have the mid-level features extracted, they can be recombined and on the fly for each individual tasks. So that's my overall vision and agenda, and I'm pushing in that direction. That's the end of my talk. I'm happy to take any questions. So let me bring my video on.
Thank you so much.
Online?
Yes, thank you so much for the great talk. Questions? I have a few ones. So maybe I start with one about this graph pooling and essentially your tokens, when your tokens are superpixels. So if I understand correctly, your model, your recognition model by construction uses semantic segmentation, right? And like this hierarchy of segmentation, correct?
Yeah, so you're talking about the last work, right?
Yeah, last work, right.
So we start with breaking the image into superpixel based on low-level appearance.
Right.
And then we try to learn how should we combine them from finer to coarse. And recognition is a loss imposed at the very end on the class token.
Right.
Right.
So essentially, to be able to do the recognition, your model is constrained to do this segmentation to arrive at the recognition.
Correct.
Right?
Correct.
This helps. Of course, like this is a phenomenal idea. I love it. The semantic segmentation results are unbelievable. But my question is, does it help the recognition?
Yeah, right. So that's the last results on recognition.
Right.
We showed this. We are better, not like a whole lot, but they are better and a lot more efficient. So we are not losing on, because we try to do segmentation recognition at the same time. So the question is, are you losing on one of these? We are not. Exactly. That's the last kind of sanity check, and we are more efficient. And on the flat segmentation, we are better. But most importantly, we can do this part and whole discovery. No one can do.
I see. So segmentation helps recognition, and recognition helps segmentation in this case. So this is I see. Very nice.
So the thing is this. Yeah. Recognition helps segment. I don't think that way. I think the segmentation is a device to do better recognition. You know, because when you say segmentation better, you have some segmentation in mind. You have benchmark. You have this supervised concept like cats and dogs. I want this to go free. I want you to discover that something intrinsic to the scene. If I have a lot of data, eventually it will discover objects. You cannot have part of the cat and part of a sofa. It doesn't help you with anything, right?
Correct.
So that's my kind of like the catchphrase, you know, borrowing from Martin Luther King, right? This is segmentation of recognition, segmentation by recognition, and segmentation for recognition, right? If my final goal is not recognition, let's say 3D reconstruction, I think the segmentation learning is very different. I have a different set of jigsaw pieces. So what I have explored in this work is segmentation of recognition, and it's learned completely by recognition. And when finally the segmentation emerges, it's good for recognition. Because I discover part and whole semantics. Anything that's it go beyond coarse recognition, you need that. If you want to be more flexible, if you want to be more discriminative, generalizable, you need those parts, conceptual parts.
Absolutely. I mean, that idea existed in the computer vision community for a long time, right? Like using parts and like decomposing an object into its parts, and that should help with the recognition, and your results are supporting that. So that's phenomenal, right? And everything before was implicit, and this like we a lot of the work in the literature assumed that, okay, a deep neural network is going to implicitly learn these relationships. But now with this last work that you showed, everything is explicit, right? Like, yes, it's learning, but it's explicitly constructed to learn that segmentation to be able to do the recognition. So that's pretty cool. Yep.
Yeah. And another thing I want to emphasize, people talk about data-driven statistical learning, right? In my mind, you can see the images going in stacks, right? All these training data. All the labels, they themselves don't mean anything unless, you know, doing clip, you have this language knowledge comes in. If they're treated as a label in a purely computer vision manner, they are just labeled to bind different images together. What I want to impose is a horizontal connection internal to the model. I want the internal parsing to be consistent. And I think this is a very strong cue. You know, the structure in learning.
Fantastic. Any other questions? Yep.
Yeah, Tyler.
Yeah, great talk. Thanks a lot. I guess somewhat of a follow-up question there. You just mentioned like if changing recognition to a different type of task that the hierarchical segmentation would likely change. And was this something that you had investigated on any data set that does have different tasks than comparing what segmentations are learned?
So I can imagine if I'm training with Coco versus training on a dense pose. Dense pose only focus on the body decomposition, torso, legs, arms, and everything else is just background, right? Versus something you want to say cats and dogs, all these semantic segmentation, right? I think if you are trained under such a criteria, I think the internal jigsaw pieces will be very different.
So do you think it's only maybe the higher level?
But I would say the following though. I think if we have a gigantic data set, if I have all kind of concepts, in the end, all these jigsaw pieces will be kind of, they may have some variation. That's why another thing I like the analogy with jigsaw pieces is that, I have kids, sometimes you buy this from Lego, sometimes they're different brand. They all have a different components. But at the end of the day, you can always use these components to build anything you like. It doesn't really matter that much. And I think if you have enough diversity, all the collection of these pieces can support different recognition tasks equally well. The diversity will help, just like all these self-supervised learning work, right? If you have a larger data set, you learn a representation that's very adaptable to downstream tasks. If you have a small, then it may have some degeneracy. It kind of latch onto something that's specific for the task. If there's enough diversity, I don't think it matters.
Okay, yeah, also like the analogy. Thanks.
Fantastic. So if there are no more questions, thank you so much for a great talk, Stella. I think we all learned a lot from you. We really appreciate the time, especially between iClear and CVPR. So in this time constraint that you were willing to come and give this wonderful talk to us. Thank you again for being here today. And I encourage everyone, if you have additional questions, please reach out to Stella and send her an email. Thank you again, Stella.
Thank you. And good luck with everybody's iClear and CVPR submissions.
Thank you.
Thank you for coming. Bye.
Talk to you later. Bye.